Now, Gwyn sort of set the scene for our closing keynote. So we're joining the dots from Gwyn's presentation through to Kevin Hand's talk, and we're going to move to exploring the oceans of other worlds. So I'll introduce Kevin Hand from NASA, who's going to talk to us about ocean worlds of the outer solar system.
Thank you, Rolf, and thank you to this group for inviting me to be here. It's a real pleasure, and I don't often get to come to small, intimate meetings like this with such a diverse group of people, and so this has been a very exciting day. For much of human history, we have been explorers of continents, seekers of rocks and planters of flags. For the most part, the ocean has just gotten in the way, with the exception of a dedicated, persistent few, many of whom are gathered here today. I think that in the century to come, we really are looking at a new age of ocean exploration. A new age of ocean exploration on Earth and beyond. And that new age of ocean exploration on Earth will be motivated by many of the things we've been discussing today. A desire to better understand the lungs of our planet, as Bob Ballard likes to say, to better understand our ocean as a precious resource. When it comes to the oceans beyond Earth, however, the question becomes one of whether or not we are alone in the universe. Indeed, the question of whether or not we are alone in the universe is, in part, the story of this beautiful blue little dot, our own ocean world, reaching out into our solar system, looking for signs of life on potentially habitable worlds beyond Earth. This diagram shows you each of the robotic vehicles that we have launched beyond Earth. The brighter colors show the spacecraft that succeeded, the darker colors show the failures. Each of those lines represents our effort to explore our own solar system. And one of the perhaps lesser appreciated results of this roughly 60 years of solar system exploration, is that we now know of roughly 6 or so moons of the outer solar system that likely harbor liquid water oceans beneath their icy shells. These are moons like Europa, Ganymede, and Callisto, moons of Jupiter, Titan and Enceladus, 2 moons of Saturn, and possibly even Neptune's curious moon Triton may have a liquid water and ammonia ocean beneath its icy shell. These are oceans that are there today and, in some cases, have likely persisted for much of the history of the solar system. These ocean worlds, these moons of the outer solar system that harbor oceans, are really kind of changing the framework for habitability. In the early days of astronomy and planetary science, there was this kind of Goldilocks scenario of, in order for a world to be habitable, you had to be at just the right distance from your parent star, such that you could maintain a liquid water ocean in contact with a nice thick atmosphere, and then you could give rise to life and become a habitable planet. If you were too close to your parent star, you were too hot, like Venus. If you were too far away from your parent star, you were too cold, like Mars. You had to be at just the right distance, that Earth-Sun distance, in order for your planet to be habitable. But what these moons of the outer solar system are telling us is that this is kind of an old Goldilocks. There's a new Goldilocks for habitability, and it's a Goldilocks where the energy for maintaining liquid water oceans is provided and sustained by the tidal energy tug and pull as these moons go around their massive primaries. And there's no better example of this than Io, Jupiter's innermost large moon. Io is the most volcanically active body in our solar system. What you're seeing towards the northern region of Io there is a volcanic plume erupting. There are likely volcanoes erupting on Io right now. Io is more volcanically active than the Earth. And it is so volcanically active because it orbits Jupiter and gets tugged and squeezed, and that mechanical energy gets converted to friction and heat that then powers that volcanism. But Io is kind of like Venus in this new Goldilocks. These are the 4 large moons of Jupiter, the so-called Galilean satellites. The innermost large moon, Io, has got too much energy. It lost any water that it may have once had. The furthest out of the large moons is Callisto. Now, Callisto, we think, has a liquid water ocean, but its ocean is beneath a very thick ice shell, and its ice shell is quite old, as evidenced by all those craters. In the center, we've got Europa and Ganymede. And Europa, in particular, may occupy this new sweet spot for habitability, where it brings together just the right amount of tidal energy to maintain a liquid water ocean in contact with a rocky seafloor, overlain by a relatively thin ice shell. In the case of Europa, we think that ice shell is perhaps comparable to the Antarctic ice sheet thickness, which is about 4 kilometers, or it may be as thick as 20 kilometers. We really don't yet know. And of course, these ocean worlds with their vast quantities of liquid water are so compelling in our search for life elsewhere, because if we've learned anything about life on Earth, it's that in general, where you find liquid water, you generally find life. From life in the extreme environments of hydrothermal vents, of hot springs, of the transantarctic mountains, from life in extreme environments to life of extreme lifestyles. All life on Earth depends on liquid water. But I'd like to show this slide for another reason, and that is that for all of the diversity of life on Earth, from the craziest of microbe to the most bizarre of rock stars, we're all connected by the same fundamental tree of life. We all run on the DNA, RNA, protein paradigm. I want to find living life beyond Earth so that we can test and see whether or not the DNA, RNA, protein paradigm is the only game in town. If we rerun the clock in one of these ocean worlds, will we get DNA? Is that a convergent biochemical solution, or is there some other way to get biochemistry done? And to test that hypothesis, we need to go to places where there is liquid water today and where we can actually find life that is potentially alive today. So this evening, I'm just going to highlight 2 of these ocean worlds, Europa and Enceladus. These oceans, we think, are in contact with rocky seafloors. As a result, we think that the oceans may be chemically rich, and thus not only do they have the water needed for life, but they may also have the elements and the chemical energy to help power life. Enceladus orbits Saturn, shown here with Saturn in the background and the rings in the background also. Enceladus is a tiny moon. It's only about 500 kilometers in diameter. This, for reference, is the Great Lakes. I should have switched this over to the UK, but Enceladus is just about similar to the size of the UK. And if you take a look at Enceladus, you'll see that there's a bizarre dichotomy. The north, this is all ice, this is all water ice that you're looking at. The north is filled with craters. To a planetary scientist, that means an old surface. It's been around for a while. And in fact, the crater age dating for Enceladus' surface puts it at about 3.5 billion years in age. But to the south, you see a paucity of craters. And you see these 4 or so parallel fractures. Those we now call the Tiger Stripes. And the Cassini spacecraft has investigated the Tiger Stripes and gotten just the right geometry such that we can view what is coming out of these fractures. This is where you're supposed to ooh and ah. What you are seeing are plumes of water jetting out from Enceladus' ice shell, and we think that these plumes of water are connected to a salty, organic-rich ocean beneath a roughly 40-kilometer thick ice shell. Here you can even see the shadow of the plumes on plumes that are more distant along that south polar terrain. These plumes are erupting roughly 200 kilograms or so per second of ice and gas from that south polar region, some of which falls back on the surface, and you can see here how some of that fractured terrain becomes more subdued with time as material falls back down onto the surface. How do we know what's in that plume material? Well, the Cassini spacecraft has got two quite capable mass spectrometers on it, an ion-neutral mass spectrometer and a cosmic dust analyzer. The INMS, as it's called, sampled those plumes directly and found not only water, but also methane, simple organics, carbon monoxide, and then some fraction of more complex organics and carbon dioxide. The extent, the mass extent of that spectrometer goes out to about 100 AMU, and thus we don't necessarily know whether or not these organics are cracked from larger, perhaps much more complex organics. So for now, this is all we know about the complexity of the organics. The cosmic dust analyzer sampled the plumes and the E-ring of Saturn, which is where the plume material eventually ends up. And in that analysis, it was determined that the plumes not only contain these gases and organics, but they also contain salts. That was very exciting because just seeing the organics and gases in the plumes would not necessarily require a liquid water ocean in contact with a rocky seafloor. In fact, there was much debate about this composition and whether or not Enceladus was just some sort of glorified comet. That's no disrespect to comets. Comets are great. But to make that leap to a liquid water ocean beneath the ice really took the data set of salts in the plumes, because salts require that water-rock interaction. And so we now think that the plumes are coming up through fractures in the ice, delivering gas and some bubbled off ocean water to space. One of the most recent discoveries further advances this conclusion that Enceladus' subsurface ocean is interacting with a rocky seafloor. The cosmic dust analyzer also detected silica. Silica would not be in an ocean that is not cycling with rocks, and more specifically, we would not have a consistent supply of silica in Enceladus' ocean were its seafloor not at least somewhat hydrothermally active. And so the conclusion of the detection of silica nanoparticles in the E-ring material, which is derived from the plumes, is that Enceladus' ocean is circulating through a porous seafloor that is experiencing low temperature hydrothermalism, perhaps serpentinization, and some of that material is then making its way up through the plumes, where it can then be sampled by the Cassini spacecraft. So this is our current understanding of a cross-section of Enceladus. It's got this rocky, perhaps partially differentiated inner region, an ocean that is still being debated as to whether it's concentrated in the South Pole or whether it's global. I think the general consensus at this point is that it may well be global. But the fractures that are emanating the plumes are really only in the South Polar region. The Cassini spacecraft just recently made its last flyby of Enceladus. And so that is all the data we will have until another spacecraft reaches the launch pad and heads out towards Saturn. And right now, we do not have a mission that is on the books to get to the launch pad. That is part of what we are trying to advance at JPL and within the planetary science program. So for now, Enceladus has gone quiet. Now I'd like to take you to Europa. Europa is a much bigger moon. And one of the first things you'll notice are all these fractures and essentially no craters. Europa's surface is tens of millions to perhaps 100 million years in age. That's comparable to the oceanic crust here on Earth. And those fractures that you see, we think are fractures made by the tidal tug and pull and flexing as Europa orbits Jupiter. Europa is about the size of our moon, but though we have an experience of the tides on Earth, imagine your Europa, you're orbiting Jupiter, which is some 318 times as massive as the Earth. That tidal tug and pull really provides perhaps a torturous experience for Europa's interior. And it's all that energy that helps maintain that liquid water ocean. How much water is in Europa's ocean? Well, I'll provide the following comparison. This is a beautiful graphic that was made by colleagues at Woods Hole. And what they've done is taken all of Earth's ocean water and rolled it up into that beautiful blue marble. And of course, the first thing that you should appreciate is that our oceans are fragile and limited. Despite the fact that our ocean covers much of our surface, we really have quite a shallow ocean. On average, it's 4 kilometers in depth, and at the greatest depth, it's 11 kilometers deep. If you do a similar roll-up of all Europa's water, you yield a blue marble that contains 2 to 3 times the volume of all the liquid water found in our oceans. How can that be? How could such a small world contain so much water? Well, Europa's ocean is global, and we think it's about 100 kilometers in depth. And so the cross-section for Europa looks something like this. We've got that rocky seafloor, 100 kilometers of ocean, and then this ice shell that may be a few to perhaps 10 or more kilometers in thickness. And we think that that ice shell, as shown there by the colors convecting up, we think that the ice shell itself may provide a window into Europa's ocean. This is a close-up of Europa's surface, showing some of those fractures in higher resolution. And one of the great debates that's persisted in Europa science is what is this discoloration? What is the nature of that material that you find along some of the fractures and along some of the features that appear to be coming through and up from the ice shell and the depths of the ice shell? Some have argued that it's sulfuric acid, by merit of sulfur coming from Io's volcanoes. Others have argued that it's got to be salts coming from the ocean below. Well, one of the things that my colleague Bob Carlson and I did in our lab not too long ago is we tested the hypothesis of whether or not this yellow, red, brown material could in fact be oceanic salts. Now, since we can't wake up in the morning and go to Europa, we are constrained to the task of building Europa in the lab. And what I'm showing you here is what we like to call our Europa in a can. And so on the end there, this is a helium-compressed cryostat that then sends a little cold finger into this ultra-high vacuum chamber. And in these experiments, what we did was looked at salts. This is sodium chloride. Now, unfortunately, the universe conspires against us because chloride salts, the predominant ocean salts, are actually not vibrationally active in the infrared, and so we can't do a lot to remote sense them. And they look in the visible just like, say, water ice. So we tested, we put these in the chamber, and one thing about Europa's surface is that it is bombarded by high-energy electrons and ions and protons that are coming from the Jovian magnetosphere. And so we introduce these salts into the chamber, turn on the electron gun, get them down to Europa temperatures and pressures, which is about 100 Kelvin and 10 to the minus 9 or so torr. We did this with salt grains, and we did it with salt brine. In this video, I'm pumping down the chamber, and you can see that saturated brine bubbling out as all the water gets pumped away by the vacuum, leaving behind a salt evaporite. Once all that water was gone, I turned on the electron gun, and that's what you're seeing here. I'm rastering back the electron gun so you can actually see it, but normally I just keep it going fast so that the whole surface just looks slightly blue. So now this material has been exposed to Europa's surface conditions. When we pulled it out, what we saw was that the salt grains turned a distinct caramel brown. And up close, you could see that many of the grains that were right on the surface of that material turned that darker brown. And so too with the brine evaporite turned to this odd yellowish brown material. This ends up matching, at least in the visible, somewhat well with the discoloration that we see around Europa's fractures and in the regions where we think new material might be coming up. And so what I think we're seeing when we look at some of the highest resolution images of Europa, and this is a black and white image, and the Galileo spacecraft only returned a few postage stamps of this. So everything you see here in white is water ice. The grays and the blacks, we don't really know what that material is, but I think that much of it is likely salt that is falling out as essentially talus on these cliff edges, collecting into the valleys below, perhaps mixing with some sulfur from volcanism on Io. But this material may also perhaps contain organics and microbes or some relics of any creatures that may have also been upwelled through the ice or cryovolcanically emplaced. So this talus along this roughly 100-meter cliff could be rich in salts, organics, and possibly signs of life in that ocean below. But now I want to connect these ocean worlds with our own ocean. As I mentioned, I think we're embarking on this new age of ocean exploration, and it will connect our ocean with these ocean worlds like Europa and Enceladus. And there's a wonderful bridge here. The science of these ocean worlds beyond Earth really focuses on this question of searching for living life to really test the biology hypothesis and see whether or not the origin of life is easy or hard, and if a second origin also leads to the DNA, RNA, protein paradigm, or if some other biochemistry is possible. But even in the absence of life, we will engage in sort of a comparative oceanography across planets and moons. On the technology side, part of what's making this possible is that NASA is developing new launch vehicles, new propulsion, landing, and instrumentation that can help address these questions of oceanography here and beyond. We've got a host of different mission options, but the key thing for this audience is that there's really a win-win that will start to bridge the technological development of devices that we can use to explore throughout our ocean here on Earth and in some of the deepest depths of our ocean. And when we develop and build those capabilities as a precursor to future NASA missions, we are getting the win-win of doing science on Earth as we build that bridge to these ocean worlds. Just to put some of that in context, here's a pressure versus depth diagram of Earth, Europa, and Enceladus. On Earth, if you go 1 kilometer down, you're at a pressure equivalent of about 7 kilometers within Europa's ice shell. At Enceladus, you're 100 kilometers down, so you're basically at the bottom of Enceladus' ocean. If you go down to the Mariana Trench, the deepest depths of our ocean, you're at about 80 kilometers down in Europa, so that's well beneath the ice shell and perhaps as deep as the sea floor. Now, of course, on Earth, several manned submersibles have made it to depths that could, in theory, survive on these distant ocean worlds. The big challenge, of course, would be actually getting those vehicles there, but that's a different story. But now I want to just share with you a few technologies that I've had the privilege of participating in, and these are technologies that were funded in part as robotic vehicles that would someday go to Europa or Enceladus, but we're getting good science done here on Earth. And the first is a robotic vehicle that we use to study thermal karst lakes up in Alaska. These are beautiful systems where each winter these lakes freeze over, and some fraction of these lakes are seeping out methane. That methane then gets trapped in the ice, and some of the microbes eat that methane, and some of the microbes produce more methane. And so as a dynamic but then encapsulated ecosystem, they're very interesting, both in the context of fundamental microbiology, but also the Earth's greenhouse gas inventory. We know that the methane gets trapped because we can actually chip through these holes and light it on fire. And these lakes are quite shallow. And so when I was first up there with a team a number of years ago, we were thinking, well, darn it, we're here just making a point measurement. Wouldn't it be great if we could release a submersible, have it map out these lakes, tell us where the methane's coming from, mark the seasonal changes, make your classic sort of limnology measurements, and then we can come back in the spring and pick the thing up. Well, as you all well appreciate, doing that with a submersible is very energy expensive. You've got thrusters, you've got station keeping. A lot of tax goes into making a long-term vehicle. Well, thankfully, being at JPL, I get to work with brilliant engineers, some of whom help design vehicles like this, which operates for incredibly long periods of time on different worlds. And so some of my friends, some of my engineering friends were up there with me, and we kind of had this collective aha of, well, you know what would be more efficient and perhaps a better design for this particular environment is, why don't we make a vehicle that's a rover, but instead of roving on the ground, have it rove on the ice. So the rover would be buoyant, pushing up against the ice-water interface. And so that, of course, is what we ended up designing. This is our Buoyant Rover for under-ice exploration. And the simplest rover design is a two-wheeled vehicle with a tail. This is also quite good because in our future designs, we will have deployable wheels and a bending tail that can allow us to go down through a borehole that's drilled or hot water melted through ice. So now I'd like to share with you a little video that National Geographic put together about this vehicle.
The rover that our team has developed is an early precursor of something that we may someday fly to Europa. The Buoyant Rover for under-ice exploration is designed to float on the other side of the ice and to rove as if the other side of the ice is the ground. These ecosystems up in Alaska, these lakes that freeze over every year and then freeze down, they're just one example of life in an extreme environment that can help guide us in assessing whether or not a world like Europa could harbor life. We cut a hole in the ice, put the rover underneath the ice, and then left it out there so it would rove around. And we went back to a nice warm Quonset hut, and our team was even able to hand over control to engineers down in JPL. And so we think this truly was the first time ever that an underwater, under ice, untethered vehicle has been operated through satellite link. Our work has this wonderful marriage of advancing our understanding of what's happening on our own planet while simultaneously feeding forward into our exploration of potentially habitable worlds beyond Earth.
So for those of you that are curious, the communication was done, in this case, with a 900 megahertz signal that was transmitted through the tail, through the ice, to an Iridium base station that then communicated with the Iridium network and then was sent back down to JPL or to us in our Quonset hut. We've now, in version 3.0 of this vehicle, put one of Woods Hole's small acoustic modems on it. That gives us much greater range. The second vehicle I briefly want to touch on, I had no hand in building, but Kevin Hardy here in the audience, shown there, he built this vehicle as part of James Cameron's deep sea Challenger mission to the Mariana Trench. And I had the great pleasure of being a scientist who helped out on that mission, and Kevin's deep ocean landers returned this stunning imagery and video footage of the deepest depths of our ocean, showing this incredibly active ecosystem. I don't have time to go into it today, but one of the amazing things about working with the deep ocean community and with frankly, the ocean exploration community is that I think a lot of low-hanging fruit really exists for institutions like the Jet Propulsion Laboratory, which really specialize in miniaturization and systems engineering to help bring the kind of verification and validation and testing and autonomy to the exploration of our ocean depths. So where are we going? What is the future of our exploration of these ocean worlds beyond Earth? Well, on the books, we have a mission called the Europa Multiple Flyby mission. It was formerly known as Europa Clipper. And this mission will hopefully make it to the launch pad in 2022. It will reach the Jovian system in the mid to late 2020s. It will fly by Europa, making some 45 flybys as it orbits Jupiter and dips in and out of the radiation. But the real dream of dreams is the following. We'll have a vehicle that will get dropped off from a mothership. This vehicle will have enough autonomy and onboard intelligence to do the terrain relative navigation that Steve talked about. It will also have hazard avoidance and science target acquisition capabilities on it. It will find a nice flat spot on Europa's surface. It will then deploy a melt probe with some energy source on the front. That melt probe will then leave behind a tether to relay data back up to the surface. Once that probe reaches the ice-water interface, it will get rid of the nose cone and deploy an autonomous underwater vehicle, which maybe some of you would design. This autonomous underwater vehicle would not be able to be joysticked from JPL. It would have to navigate to the ocean seafloor of Europa, where hopefully, in this Hollywood version, it would find hydrothermal vents, and it would make contact with mushy jellyfish-like creatures in this distant ocean. So that's the dream of dreams of our ultimate roadmap for where we would like this kind of exploration to go. We're just at the earliest stages of it. But I'll close with what is my favorite image from the history of space exploration. It's an image carved by none other than Galileo himself, an image carved over 400 years ago. At the center of that image is Jupiter, the wheel shape there. And around Jupiter, Galileo drew out these 4 little bright dots that he observed night after night. Those 4 little bright dots, he thought, were initially stars. He just figured that with his telescope, he was able to see new stars behind Jupiter. And Galileo, not being a fool, named them the stars of Medici, because the Medici family was funding his research, and so he wanted to keep the funding going. But with each night, he saw that the stars moved, and of course that then led to the conclusion that these were moons of Jupiter revolving around Jupiter, which was heretical at the time and gave him big problems with the Spanish Inquisition. But with Galileo's discovery of mountains on our moon, of the phases of Venus, and perhaps most significantly the moons of Jupiter, Galileo helped put the final nail in the coffin of Aristotelian cosmology and opened the door to the Copernican revolution. And in the decades that would follow Galileo, we would come to appreciate that the laws of physics apply not just here on Earth, but also to worlds and wonders beyond the Earth. And then with the advent of new spectroscopic techniques, we would come to appreciate that the principles of chemistry apply not just on Earth, but also to worlds and wonders beyond the Earth. And with the advent of the robotic age of space exploration, we will come to appreciate that the principles of geology apply not just here, but also to worlds beyond Earth. But when it comes to that fourth fundamental science, when it comes to biology, when it comes to that bizarre little phenomenon that we know and love and call life, we have yet to make that leap. We don't yet know whether or not biology works beyond Earth. We have every reason to believe that it should, and we can make a valid hypothesis that it will be found in these ocean worlds beyond Earth, but we have yet to do that experiment. And part of what excites me about the time period in which we live, and part of what I think we will accomplish in the coming decades and century, is that we will do the experiments. We now have the tools and technology to go out there and see whether or not we do, in fact, live in a biological universe or if we are alone. And so it's my hope that some 400 years from now, our descendants will look back at our time and they will say, it was then, it was during that time in humanity's history when they did the experiments that brought our universe to life. Thank you very much.